So for this video, we're going to look at the cross product. This is, we're going to look at the algebraic version and the geometric version of it. So suppose we have two vectors, A, which is given by A1, A2, and A3, and B, which is given by B1, B2, and B3. We want to find a third vector, C, that is perpendicular to both of them. So what we need to find is C, which is given by C1, C2, C3, such that A dot C from the dot product is 0 and B dot C is also 0. Now, I'm not going to work through the entire proof here, so pause the video. You can work through it yourself. But when we get to the very end here, we're going to find that we have the C vector that we were looking for having been defined like this. And this is important because this is the result. When we work through this, this is our result, and this is the cross product, A cross B. Now, that's kind of hard to remember, so sometimes we work with the algebraic version, which is the determinant form. So algebraically, we can set this up in a matrix. We set it up with the I, J, and K vectors crossed on the first row, and then A1, A1, A2, A3 are A vector in the second row and our B vector in the third row. And when we work it out with our determinants, we can remember how we do determinants of a 3x3 matrix. We break them down to a 2x2 matrix using our first position I. We eliminate that row and that column, and we have the determinant of the remaining factors. So now this is A2 minus B3, A2 times B3 minus A3 minus B2, and that's how we get our first one, and so on. Now we have to be careful right here that we don't miss that negative in the determinant. So our cofactors are always positive, negative, positive as we go across, so that the second term here with the J shows up with a negative. Now, if we do that, we find out we have the same exact answer as above. So we have calculated our cross product. So let's look at an example of how this works. And if we set it up, we have I, again, I, J, and K across the top row, and 1I plus 3J plus 4K. So that's 1, 3, and 4. So it's just the coefficients. And then in B, in the bottom row, we have 2, 7, minus 5. So to work this out, we have I, create our 2x2 matrix by ignoring the first column and the first row, because that's where the I was located. And we get 3, 7, the 4 here, and the negative 5. Remember that we have the J, we have the negative there, because our cofactor in this column is going to be negative. So again, ignore the column that J is in, ignore the row, and we get 1, 4, 2, and negative 5. And finally for K, we're going to do the same thing. Ignore that row, ignore that column. Our cofactor is positive, and we get 1, 3, 2, and 7. And when we finally work this out, we can do our determinants pretty easily on a 2x2 matrix. It's literally just crossing with multiplication. So 3 times negative 5, that's negative 15, minus 7 times 4, which is 28, minus the J factor. We have 1 times negative 5 is negative 5, minus 4 times 2, which is 8. And then the K factor. 1 times 7 is 7, minus 3 times 2, which is 6. And if we simplify all that, we get negative 43I minus, well, we would have minus 13 here, but it's a minus, so we get a positive 13J. And then 7 minus 6 is, of course, 1. And that is our cross product of those two vectors. All right, so let's talk about a few properties of the cross product. One is that if we cross a vector by itself, the cross product is 0. is the 0 vector. So that's different than just saying 0, because 0 is just a numeral, like you would get for a dot product. This is the cross product. Make sure that we always say that this is a vector. And we can see that if we worked it out just like we did in the example, we would get A2 and A3 in this first one, A1 and A3 and A1 and A2 just like before. And you see these all work out to 0. Because remember, commutative property of multiplication. So this works out. Any vector crossed by itself is 0. A few other properties of the cross product is if you flip the order, the product is negative. And we're going to see that in a second when we talk about the right-hand rule. But if you take A cross B is equal to the opposite of B cross A. We also have, if we have this, A cross the sum of B plus C is equal to A cross B plus A cross C. And actually, there is a problem in the homework that asks you to prove that. And that is problem number 39. So you can check that out. Problem number 39, we'll ask you to do that. This one we're going to talk about in a minute. This is about the triple product, but this is another property. A dot B cross C is equal to A cross B times C. There are other products, there's other properties that we can also talk about that include talking about what happens with the scalar. What happens when we have a scalar involved? Well, let's say we have a scalar r in front of A. We want to cross that with B. Well, that scalar just falls right out and comes out in front. So that's another property of the cross product. So one special property called the right-hand rule is if we were to place two vectors, u and v, so that the tail of that vector, which is where the vector starts, coincide. So you want them to start at the same point, but they're going in different directions. And then curl your fingers. Just place your hand on the u vector with your right hand, and then curl your fingers towards the v. Which direction does your thumb land? Well, it's in the case on the left here, we're starting here with the u and the v. You can see we're moving our fingers around to get up. So this is a special property that if we were to take very simply the I times cross the j vector and do it just like in the determinant fashion that we just did, you'll find out that that becomes the k vector. This is like I, and this is j. So if you imagine the x and the y axes here, you would find that this becomes the k vector. It's in the k direction or the z direction. So the case, when we just talked about this property up here, this is also true. If you were to flip these around and say v to u, you'd notice that your thumb would have to point down. So again, if we do j cross I, that's the opposite of this one. And so now our vector is in the down position on the z vector, or the z-axis. So that's our k vector. And that's a special property here. So a couple other ones here. If we do j cross k, we're going to get I. And if we do k cross I, we get j. So they're all interrelated by these properties. So we talked about the geometric, we talked about the algebraic. Now let's talk about the geometric definition. So again, this is another proof that's been worked out. We're not going to go through every single step here. So pause it. You can work through it on your own. But what I want to draw attention to is if we start with A cross B, but we're going to find the magnitude of it. Remember, magnitude involves the square root of the square of each of the components. Well, I square them to start with. That gets rid of my square root. That's less to work with. And if we work this out, here's all the algebra here. I will point out that these in red that you can see here are actually being introduced. They weren't part of the original, but they're being introduced in a plus and a minus fashion so that we can reach this conclusion where we have a1 plus a2 plus a3 times b1 plus b2 times b3 minus this sum squared. And that gives us this. This is an important result. The magnitude of a squared, magnitude of b squared minus the dot product ab squared. Now the dot product of a times b is magnitude of a, magnitude of b, cosine. We remember that from our dot product. Well, if we're squaring that, we've got them each squared as well. And we know that if we were to factor these out, here we factored them out here, we would get 1 minus cosine squared, which we know is sine squared. Well, that leads to this final result, that a cross b, the magnitude of a cross b, is equal to the magnitude of a, magnitude of b, sine theta. And that's a geometric definition. So if I were to take a, let's just say this is our a, and this is our b, we could find the cross product if we knew what our theta was here. We could find the cross product, the magnitude of the cross product, by just taking the magnitude of a and the magnitude of b, and then finding the sine of the angle in which they create. Okay, so a couple of very fun, what I find fun, applications of this. We get the area of a parallelogram and then a volume of a parallelepiped. Parallelepiped is really just a fancy word for a rectangular solid that's been tilted. So let's start with the parallelogram. This is the magnitude of b cross c. So let's take our 2, and b cross c being the base face of that parallelogram, or parallelepiped. That's our parallelogram that we're looking at. So b cross c. Now, we need to find the cross product, of course. So b cross c is equal to, and of course we got to set up our matrix. And we have 2, 1, negative 3, and 1, 3, 2. Okay. So we're going to get 1, negative 3, 3, and 2, minus j. We get 2, negative 3, 1, 2, and of course k, we get 2, 1, 1, 3. So let's work on each one of these. So we get I is 4 minus a minus 9, so we're going to plus 9, minus j, which is 4 minus a minus 3, which is plus 3, plus k, which is 6 minus 1. When we work this out, we get 13i minus 7j plus 5k. So what's the area? Well, we got to find the magnitude. And I always start with the magnitude squared. Just makes it a lot easier to start with. And we can just square each of these components. So we get 13 squared plus a negative 7 squared plus a 5 squared. Well, 13 squared is 169 plus 49 plus 25. Now I had to grab my calculator quick and work this out. I get 243. And if I take the square root of that to get my actual area, so this is my area, it's going to be the square root of that. Square root of 243 does not really come out all that cleanly, but we do recognize that 243 is also 7 times 49. So doing so, we can also say it's 7, square root of 7. Okay. Now, the last thing that we're going to look at is called the volume of the parallelepiped, which is we also call it a triple product. I've also heard it called a box product. It's basically all the same thing, but this also has a very easy application, is that if we have all of our vectors, then we can find the triple product pretty quickly. Now, so we're going to call this B, this C, and this A, just like we did up here. And in doing so, we can find that we have P1, P2, that's going to be our B, and P2 to P4 right here we have found as BC. So A is going to be the vector from P1 to P5. So A is going from the origin being 0, 0, 0, P5 being 1, 0, 4. We can find that that's I plus 4K. We can do that pretty quickly just in our heads. All right, so now we have everything we need to know about finding the volume. So the volume, as we were told up above here, we just have our A1, A2, A3. Well, we know that to be 1, 0, and 4. We need to find B. We have B as being 2, 4, and 2. And C is just 3, 0, 0. So just like before, but now we don't have the i's anymore. We actually have numbers to work with. So our first cofactor being 1, we have 4, 2, 0, 0, minus, well, that's going to be 0 anyway, but let's fill this out. We have 2, 3, 2, and 0, plus 4 times 2, 4, 3, and 0. Well, we got a lot of zeros here. So there's 4 minus 4, 4 times 0 is 0, minus 0, another 0. Hey, there's a 6, but it's still 0 anyway. We get a 4, 0, minus 12. And somehow we end up with a volume of minus 48, which I don't think is actually correct. So we do have the, it's the volume of this is actually the total value, which is 48. So 48 is the correct answer. And this is actually problem 38 from the textbook. So that's it. That's your cross product.